Good morning or good afternoon, depending on where you are, and thank you for joining us today. I'm Jim Jones. I'm the director of CINA at George Mason University and your moderator for this panel today. I would like to thank the CINA team for all of their work, my fellow COEs for all of their efforts, and especially my co-organizers for this panel, Gina Ligon of Ensight at the University of Nebraska, Omaha, Fred Rogers of Cicada at Rutgers University, and Bill Braniff of START at the University of Maryland. My colleagues and I in the research community, to include our panelists today, spend a lot of our time trying to derive useful information from mountains of messy data. This is what some people would call a version of the big data problem. For much of our work and the use cases that we address in our research, we're especially interested in teasing out network structure from that data. So what does the network behind this data look like? How does it work? What are its strengths and weaknesses? That challenge, how to infer useful information like network structure from data, is the subject of this session. We have assembled an expert panel to help us talk through this. Today we have Carlotta Domeniconi. Dr. Domeniconi is an associate professor of computer science at George Mason University with expertise and research interests in machine learning, pattern recognition, educational data mining, and feature relevance estimation, with applications in network analysis, text mining, anomaly detection, bioinformatics, and finance. We also have Mr. Richard Takis. Mr. Takis is an analytics manager at Accenture Federal Services with expertise in data analytics for industry and government applications. His main areas of research and application include emerging internet technologies, open source data analytics, and machine learning. And finally, we have Barnett Coven. Dr. Coven is the training director, near-peer competition lead researcher, and counterterrorism lead researcher at the START COE at the University of Maryland, and his research answers pressing defense and homeland security questions in such areas as counterterrorism and transnational organized crime. We'll begin this panel with some prepared remarks from each of our panelists. Then we'll take questions from you, the audience. Please feel free at any point to submit questions in the chat box of the VEE, the Summit application in which you're viewing this session, and we'll get to as many of those questions as we can. With that, I would like to hand it off to Dr. Domeniconi. Carlotta, the floor is yours.
Thank you, Jim. Thank you very much for the introduction, and good afternoon or good morning, everyone, to all the panelists and to the audience. And thanks, Jim, for the invitation to be part of this panel. It's my pleasure to be here today. So in the next 10 minutes or so, I will highlight some of the challenges as I view them when we're dealing with discovering patterns and information from network data, and then some ideas on how to move forward with these kinds of problems. Next slide, please. All right, so what are the challenges? So adversarial networks typically pose very difficult problems and challenges to policymakers and to law enforcement officials in general. And this is due for a variety of reasons. These networks can be very large in terms of scope and size. They're typically heterogeneous. They can involve different kinds of agents. For example, the agents could be individuals, could be gangs, could be families, or could be organizations or even countries. These networks are dynamic. They change over time, and they adapt also to change to external factors, and they can present a variety of structures. Likewise, the activity which are involved in these networks can be highly complex, highly dynamic as well, and also typically what we can observe is incomplete. So given these challenges and this difficulty, it's very highly desirable to develop models that can help us understand and predict the overall trends in these networks, as well as their level dynamics. But unfortunately, in my view, the development of such models is still very much an art in its infancy. Next slide, please. So the question becomes, so what are more specifically the challenges that we need to deal with? So first and foremost, of course, is where do we get the data, the network from? So the way I view adversarial networks is as a complex system of agents or actors. As I said, this could be individuals, gangs, families, and so on. And these actors manifest behaviors, and they also engage in relationships in a web of interactions with one another. Now, these behaviors and these interactions actually give rise to macro-level phenomena, macro-level behaviors, which are very hard to predict and understand due to their complexity. So in order to develop models that are powerful and meaningful, it's really paramount that we have available information regarding these actors and their interactions. Of course, this is not an easy task, right? Because of the nature of this data, they are highly confidential and private. One of the questions is, how can we enable different organizations to jointly train models without necessarily having to share their private data? So that's one important question. Now, what are the tasks that we want these models help us in solving? Two tasks that I can definitely identify is making predictions and forecasting, but perhaps more importantly, making effective, helping us doing useful and effective intervention strategies. That is, design intervention strategies that enable to disrupt the activities associated with these networks. In order to achieve these goals, there are some requirements that this model should have. The findings and patterns that are being discovered should be explainable. They should be accompanied by explanation so that they can lead us to a deep understanding of the underlying structures in these networks. And they also need to enable us to perform what-if analysis so that effective intervention strategies can be applied. Now, keeping in mind that these networks are dynamic, of course, this is difficult because it involves understanding and forecasting basically a moving target. Next slide, please. So a lot has been done with data mining, right, and machine learning using data-driven approaches. And next slide, please. And I can highlight a few things, few tasks that we can accomplish through data-driven approaches. And these are just examples of projects that I also have worked on. So with machine learning, we can find and discover from heterogeneous data both explanatory and predictive patterns. For example, on the top right here, you see a network, a large connected components. In this case, the agents are actually financial organizations, active firms in the United States, along with their interactions. And this was part actually of a project that I did with FINRA. And what we can discover with these networks is groups of firms that highly interact with one another. You can call these communities, along with the activities that characterize such groups of firms. So these patterns also enables us to discover anomalies, anomalous groups, as long as with the anomalous behavior associated with these groups. Now, as I highlighted earlier, these networks are typically dynamic, right? So the agents engage in relationships under certain roles, but these roles are also dynamic and they change over time. So with machine learning, we can discover these roles, we can track these roles over time, and by studying the dynamics of this role, we can also make predictions, and as well as performing predictions of events. Next slide, please. So where do we take this further as we move along in this area? So I do think that today we are at the tipping point where scientists and engineers have at their disposal the computational power to run very large-scale simulations in laptops. So we are ready actually to develop complex models that can simulate the way these adversarial networks operate, enables us to study and understand their structures in order to make predictions and devise strategies for interventions. Simulations can also help us with the problem of data. We can generate simulated data. An interesting paradigm that can also be useful is federated learning. It can help us enable collaborations of organizations that can work together in jointly train these simulations in large-scale models without having to share their data. I think ensemble techniques can have an important role here, where rather than focusing on a single model, we can actually train committees of experts, and this enables us to generate robust models without having to tune to specific learning biases. For example, ensemble techniques are deployed today successfully in understanding the current pandemic and to make predictions, forecasting, and for devising effective intervention methodologies. For the purpose of providing explainable patterns, explainable findings, I think the deep learning and attention mechanism will still continue to play an important roles, as well as exemplar-based learning methodologies, which enables us to understand the portion of the networks we should pay most attention to, perhaps for developing meaningful embedding mechanism, meaningful representation of our data, as well as making predictions. So overall, the pipeline I envision is acquiring data, performing large-scale simulations of these complex systems that will enable us to analyze and study these systems, understanding their structures, and eventually making prediction and interventions. Next slide. So this is my last slide. So in the future, I do envision that hybrid approaches may play an important role, and they can offer interesting solutions to the problem. In these hybrid approaches, one can combine both data-driven machine learning techniques with domain expertise. And one example of such an hybrid approach would be a system in which machine learning and domain expertise work together to inform a large-scale agent-based model. So the way such a system can operate is that we can learn behaviors and features from known data using data-driven approaches like machine learning, and then we can use those learned behavior to inform how the agents operate, and then we can use these agents to be large, optimized agent-based models to model these criminal networks and their interactions. These kinds of systems can enable what-if analysis and can also enable predictions of sophisticated patterns that perhaps cannot be achieved by using data-driven approaches alone. And I'll stop here.
Carlotta, thank you. Fantastic introduction. It's almost as if you've also taught this material if I didn't know better. Thank you. Very good foundation. So next up is Rich Takis. So Rich, I will turn the floor over to you.
Thank you, Jim. I don't have slides to share, but quick reminder, I'm an analytics manager at Accenture Federal Services. We do a lot of contracting with the US federal government. Most of my work now is with State Department and DoD in that space, but I've been in the network science space focused on disinformation and social network analysis for about 10 years. I'm going to talk today about three kind of hard problems and how network discovery can be an enabler to kind of all these. So we talked briefly about just the scale and quantity of the data that's out there that is being pulled in for large scale analysis. But the simultaneous need to do real-time detection. So you have this real-time analytics need against huge data. The second problem is fully understanding the threat. And then the third is making sure our recommendations to decision makers are computationally sound. So data access, integration, and network kind of construction, I'll complicate this too. So the first thing, data access. So, most people get access to social media or open source data in one of three ways. You can pay for it and you get this curated, but not necessarily representative data set. It's also proprietary in a lot of tools and very difficult to export. So across the US government, we oftentimes run into a case where multiple redundant analytic platforms are being purchased for the sake of data. And that is, that's difficult to justify because we are essentially buying the same platforms over and over and over in terms of analytics because they have a slightly different data stream. The second answer to the data piece is APIs. Twitter's the most common. This being an academic, kind of hosted event, I'll just mention the student API does enable full access to the Twitter archive now, which is great for huge quality scaled research. And then scraping engines. So a lot of web drivers and Selenium, things like that are being used to gather that data. So obviously these data come in a lot of different formats. There's a lot of different data structures in here, whether it be text, imagery, video, sound, things like that. It's all potentially included in open source analysis. So integration of that data and forming networks, or integration is where the network science to me really begins. I'm going to touch on two pieces: graph databasing and machine learning based data tagging or annotation. The first one is the graph database and storage, push gets us away from the SQL schema-based databases, and kind of through both document databases into a graph database. So I use Neo4j, for instance, but there are others where a document to a schema to an expressed value in that database model is more naturally understood. It's the expressive it is more expressive of the representation of the data between them and allows recall of data fast. That said, machine learning based annotation tagging is key. We do a lot of this now in terms of pre-processing of data, just tagging different aspects of take social media posts, for instance. So a YouTube clip and an original tweet, for instance, would be labeled as a post. So kind of tagging those things moving through. This enables the cross-platform and cross-social environment integration, and also allows us to make a bunch of different types of networks. So everyone's used to this user-to-user or person-to-person network. And also form content-based networks, so user to content or narrative or keyword or whatever, and then narrative to narrative. And then we also are beginning increasingly to look at some of the real-world effects of some of these network representations on social media, network enabled effects, specifically with malware and pushing malware, much in the same way that search engine optimization was done, is done on social media platforms by organized networks. So it is really the machine learning tagging that enables us to be able to make these different network typologies. And I will note that the graph database does have a pull-in for Elasticsearch and JSON, so it can be used against traditional aspects as well. And then the last one is real-time prediction, the second one, real-time prediction. I think this is misnamed. I'll move quickly here. I think a forecasting is needed. By the time something becomes viral in this environment, it is too late. The effects of the network are exponential and usually rising by then. And in terms of decision makers, real time for them means, especially in the national security setting, enough time to assess the threat, develop a strategy, gather resources, and execute mitigation. So real time to them really means, as long as that takes, and that's incredibly important in terms of forecasting. And then understanding the threat. So networks are created for intent. We've all seen the narrative pumping in SEO that have been used by networks and social media environments in the past. Touch on three quick examples of why that's not necessarily how we should be looking at it in terms of content-based analysis. In 2018, we did a project for the midterm elections that ended up shutting down about 300,000 silent bots, which had been laid and prepared, friendships established, but no content. So they wouldn't have popped up on any analysis. The second one I want to touch on is SEO, or search engine optimization, being done by Russian news outlets that also involve bit.ly links and other shortened URLs in the post that direct to a bounce site that will distribute malware to a user's device. So there is real-world impact from that. And then lastly, in terms of real-world impact, we did a project with USDA that enabled us to kind of counter a network effect of a narrative being spread amongst migrant labor that comes to the United States to help bring in crops. So a lot of different aspects can be used against this, but this methodology of graph databasing, machine learning, tagging, and having a lot of network typologies really helped understand that. So lastly, like the computational response, all too often the best response is no response. And I know that's a counterfactual to prove, but oftentimes, especially from a government perspective, engaging with a topic only makes it worse. I will mention that having access to things like Turgams and Ergams and Bayes-based networks with conditional probability inference help that out a lot. but oftentimes, unfortunately, the answer is to let something pass in that respect. So I will pause there.
Great, Rich. Thank you very much. That's a great foundation, and you kind of hit that where the rubber meets the road piece, which very useful. Thank you. We'll continue that. Finally, for some prepared remarks, we have Dr. Coven. So Barnett, the floor is yours.
Excellent. Thank you so much. Good afternoon or good morning to everyone listening in. I really appreciate your time and attention. I want to run you through a project that used a big data source and used sort of network discovery tools for a sort of real world Homeland Security national defense application. This work was done in support of U.S. Special Operations Command, but with a heavy role played by the Department of Homeland Security, their Office of University Programs. And so with that, this program looked at sort of gray zone conflict. And so I'll start with giving you a quick definition. This is the definition of what we were working with according to U.S. Special Operations Command at the time. I won't read the whole definition since it's up there on the slide, but I think the critical aspects are bolded for you. A bias towards multiple elements or instruments of national power. So this is not your traditional kinetic military engagement, but there's much more sort of emphasis placed on diplomatic, informational, economic, etc. levers of national power. Like any type of engagement, the goal is to obtain some type of political or security objectives. But critically here, these types of gray zone engagements are ambiguous in nature or designed to cloud attribution, i.e. it's not obvious or at least definitive that it's the Russians who are the aggressor here, for example. And similarly, they are designed to stay below the threshold of sort of a declared shooting war or open armed conflict for the most part. Anyway, that's what we're talking about. Next slide, please. And so the command and DHS wanted to know if there was any type of way to do sort of strategic indications and warnings for gray zone conflict, i.e. if we're in one of these engagements and we see certain types of activities, what can we expect next? And so we built something called a Bayesian belief network model. And in order to sort of, since I know we have sort of a wide array of audience members, most of you are probably familiar with this model, even if you've never heard the terminology before, because my guess is you have one of these, an iPhone or an Android or a Google phone or something of the sort that has autocorrect. And you can think of this the model we built almost like how your autocorrect works. So when you take your brand new cell phone, smartphone out of the box, it's pre-programmed with an English language dictionary, and in all likelihood, dictionaries in multiple different languages. So it's able to, right out of the box, correct your spelling, correct your grammar, because it understands grammar and spelling rules. But over time, it learns your unique vernacular. So I use certain words when I speak. My boss pointed out to me that I like to say insofar as a lot. I never knew that, but apparently I do. Anyway, insofar as that's the case, the iPhone sort of recognizes that over time. And as you start typing, it realizes that, hey, these combinations of words or this pattern matches 10 others where you've used insofar as the next word or phrase, and it'll suggest that. And you've probably seen this when you're typing a text message or an email on your phone, that it sort of suggests what you might want to say next. And that's what's going on here. It's understanding sort of the network relationship between words and phrases based on an understanding of grammar rules and spelling that really doesn't change all that quickly, but also based on sort of your unique speech and text patterns. And so that's more or less what we did here. Except what we were mapping was sort of the interplay between events undertaken by various different actors within different governments, across a dime-fill spectrum. So diplomatic, informational, military, economic, law enforcement, financial, and we actually added to dime-fill and added a few of our own categories. But regardless, that's what we did. At its sort of base level, a Bayesian belief network uses abductive reasoning. That's inference to the best explanation. And if there are any medical doctors in the room, you're familiar with this. You're taught in your first year as a clinician that if you hear hoofbeats, think horses, not zebras. That's probably a good sort of gut reaction unless you're practicing medicine in Africa. The same applies here. It's sort of looking at what the best, most probable explanation is given the events that occurred prior in sort of this network grouping of potential Russian activities. And so all we're doing is calculating the probability of various different things occurring given their interconnectedness with various different other types of actions. And it's using Bayesian calculus, but I won't go through the math here unless anyone really wants. The nice thing about this is it can handle really complex dependencies. If there's anyone in the audience who learned English as an adult, you know how complicated grammar rules are for the English language. So it works there, but it also works with sort of complex forms of hybrid warfare, as we found out. Next slide, please. And so we started off with an extremely basic model. We just wanted to predict sort of gray zone events based on some knowledge of the type of source. So is this Russian military intelligence versus the Russian Ministry of Foreign Affairs versus non-state proxies that have close linkages with the Russian government, and so on and so forth. Who was the target of the action? Was this the population of eastern Ukraine and, say, the Donbass? Was it the governing elite in Kiev? Or was it Western publics whose governments may be contemplating intervention on the Ukrainians' behalf back home in Paris or in New York or Washington, D.C. or wherever? And then finally, was the sort of event kinetic in nature, right? Was this a denouncement by the Ministry of Foreign Affairs, or was this an artillery duel? The latter obviously being the kinetic event, a kinetic event. Next slide, please. Oh, and I'm sorry, I should have mentioned on the last slide, but no need to go back. We used a massive sort of data source called the Worldwide Integrated Crisis Early Warning System, which is a text-to-data platform that's created through automated means using sort of machine learning AI and natural language processing by Lockheed Martin Corporation for Special Operations Command and various other US government end users. Anyway, here's our model, basically what I described in the last slide, but in case anyone's more of a visual person or likes to see an equation, there you go. In the interest of time, I'm not going to unpack this more, but I'm happy to during the Q&A if anyone's interested. Next slide, please. And so here are the results, and admittedly, this took us a long time to get results this decent. We spent about a year doing this, and unlike the last presentation, unlike Rich's remarks, we weren't trying to do this in real time. We were trying to come up with a sort of proof of concept, and then eventually the goal would be to get this into real time. But regardless, I was pretty pleased with the results we got. The overall predictive accuracy for sort of black zone and white zone events and out of sample prediction was in the mid 80% range. For gray zone events, which we should expect to be harder to accurately predict, given that in the gray zone, the adversary or the competitor is trying to obscure sort of reality and introduce ambiguity, our predictive accuracy was lower at a little over 75%. But I think that's still pretty decent, right? For most policymakers, if I can get them something better than a flip of a coin, and if I can do it fast enough, that's a good day. So I was quite pleased even with that sort of 75% predictive accuracy for gray events. Next slide, please. Here's just a breakdown of sort of the effect that various different nodes had on the predictive, on the sort of predictions that we came up with. And what you can see very clearly here is that perhaps the most consequential node is whether or not the previous Russian engagement or engagements were kinetic or non-kinetic in nature. Although you can see that all of these nodes, for the most part, did prove reasonably consequential to our overall outcome or our overall prediction. Next slide, please. Here's just a graphical depiction of some of what we saw, and this is a kernel density plot of predicted gray events. And here's the really interesting thing. And I didn't show sort of the Western targets of sort of Russian messaging. I'm only showing Ukraine here. But most of sort of the gray behavior turned out to be non-kinetic in nature and targeting sort of the capital, Kiev, targeting sort of Ukraine's senior political leadership. We had a relative sparsity of gray events in sort of eastern Ukraine, over in sort of the right center side of the image, where most of the actual altercation was occurring. And then a real paucity of events down in sort of the lower right side in the Crimean Peninsula, although that is simply explained by the fact that the conflict in Crimea started and ended in extremely short order, right? Russian forces invaded, and they had a referendum within a month on annexation of the Crimean Peninsula. So the sparsity of events in Crimea should not be sort of given too much weight. Next slide, please. And so I think we came up with sort of three key results out of this modeling. I think the first one is perhaps by far the most important. There was a relative paucity of kinetic events in Ukraine. And indeed, in the period we looked at, which was 2014 to 2016, 79.2, don't quote me on the exact number, it was 79 point something % of all events were non-kinetic in nature, occurring on the diplomatic, informational, etc. Instruments of power. Another just over 20% were kinetic in nature. And this tracked exactly with what General Valery Gerasimov, the chief of staff of the Russian armed forces, observed years prior was perhaps the appropriate balance of military to non-military force to achieve strategic aims in the 21st century. Specifically, he said that the appropriate balance was perhaps 4-to-1 in favor of non-military instruments of national power. Now, Gerasimov doctrine really isn't a doctrine, and it's been horribly misinterpreted by sort of Western academics. That is something I can spend 2 hours talking about if anyone's interested, but I will table it there. But regardless, Gerasimov's observations were actually borne out in the modeling we did, even if he was talking about how he perceived the West targeting Russia as opposed to vice versa. The other thing that was really apparent in some of our modeling, in actually digging into some of the Russian choices and doing some qualitative work on why they chose different narratives and so on and so forth, there was that international sort of concerns about how their actions would be viewed internationally, which makes a ton of sense in terms of gray zone conflict. You want to keep this ambiguous to sort of limit the clear casus belli for sort of Western democracies to latch onto and justify really strong reactions to Russian aggression. But we also found that there were real domestic legitimacy concerns, which admittedly some political scientists had noted in Russia in previous conflicts, but that we don't tend to think of, right? We know from the Vietnam War in the US setting onward that as soon as American personnel start getting injured or killed overseas, public support for overseas military engagements diminishes rapidly. It seems, though, in looking at some of the messaging and looking at sort of how some of the messaging was used, both including to internal audiences in Russia, that there was a real concern amongst the Kremlin that that might also be the case in Russia, despite its less than democratic status. And then finally, we modeled the behavior of not just Russian government actors, but I think, as I mentioned, sort of violent non-state actors that were proxies, or at least supported by Russia. And we noticed that they were far less adept at sort of responding in a coherent manner and sort of correctly interpreting their sort of counterparts' behavior and coming up with a well-sequenced sort of playbook. So Russia's sort of playbook, if you will, in terms of the integration of these different instruments of national power was far easier to model than, say, some random pro-Russian insurgent group in eastern Ukraine, although perhaps that's not all that surprising. That said, the closer those sort of pro-Russian extremist groups in Ukraine were to Russia, i.e. the more they were under the yoke of the Russian state, the better they did, the easier they were to model because they seemed to be more closely following sort of the Russian playbook, if you will. Next slide, please. And this isn't some random abstract project where we said, hey, we can do some cool predictions and whatnot. This actually has real world implications. It not only allows sort of the US government potentially to better sort of predict what's going to happen next and sort of forestall competitors like Russia or Chinese aggression. And indeed, we did this for 3 different cases. The Russian case was just the one we spent the most time on, so that's what I'm presenting here. But it also gave us a sense of sort of opportunities for improvement in US responses. And so one thing we saw really, really clearly was there was a synergistic sort of power to integrating non-military and military instruments of national power. And arguably, the US government should be doing precisely the same thing in their response. And so here's a quick article I penned. This is not US government policy. This was not part of the funded project, but sort of me extrapolating based on the data. If you really want to help Ukraine and impose cost on Russia, figure out what they need militarily. And the US government did do that. They realized Ukraine was massively outgunned when it came to sort of heavy armor, and that Ukraine needed anti-tank guided munitions. And eventually the US Congress authorized the provision of Javelin anti-tank guided munitions to the Ukrainians. That does some damage on the battlefield at the tactical level. You destroy a $10 million piece of Russian military hardware. Okay, that's not nothing. but it doesn't really translate up into strategically desirable effects. Could you, however, take a card out of sort of the Russian playbook and integrate those military victories against Russian armored forces with an influence operation or an operation in the influence and information environment that sort of messages back to the casualty-averse Russian people that their forces are fighting and dying in Ukraine, and therefore massively amplify the effects? And it turns out you can do this using open source information. The photo on the far right is a medal for meritorious service in combat. They are individually numbered, so you have a good sense of how many there are. And I obtained this from VK, the Russian version of Facebook, if you will. It is now, by the way, following this research, and that by others like me, illegal under Russian law to post military medals to VK, but that's another story. So you've got the information you need. You can spin a narrative. And fortunately, in Russia, there are groups like the Mothers of the Committees of Soldiers organizations that have a vested interest in sort of unmasking the Kremlin's secret wars that Russian children are dying fighting in. So you have everything you need to sort of use this model, see what worked in Russia, predict what's next, but also perhaps use some of the insights to inform a more integrated response on the USG's part. And by the way, we never did the last bit of what I proposed here. Next slide, please. With that next slide, while we're queuing it up, I will just, we got rid of the question, the thank you slide. But thank you all so much for taking the time to listen to me. I'll pause there and make sure we have ample time for Q&A discussion.
Barnett, thank you. That was excellent. Very useful to see a detailed kind of hard example like that. I spent a lot of time with BBNs, with Bayesian networks, and that's one of the best, clear, simple explanations I've ever heard. Thank you. Also, I think I might have survived first year of medical school if I knew it was just telling zebras from horses. Who knew? Thought it was harder than that, but thank you very much. So at this point, we'll move into some questions and answers from the panel. I'll invite everyone to remind you, if you'd like to ask a question, please post it in the chat box in the VEE and the event, the application where you're watching this video. And we'll get to as many of those as we can. One to start with, and I'm going to toss this first to Carlotta and then ask for the other two panelists to comment if they have things to add. This is a data question, Carlotta, and the question is, what are the kinds of data, private or public, that university researchers can get access to analyze, discover networks, and do this kind of research on?
Excellent questions, and that's it's actually one of the major issues, especially if the context is criminal networks and adversarial networks. So I have been, for example, in a conversation with the FBI, and they do have a data available that enables us to build some of the networks on the past cases, essentially, that have been already, resolved, and therefore they're, public domain. And typically this data involves text data, narratives, from which one can construct network data. I do want to emphasize the fact that real data can also be integrated with simulated data, and that can perhaps fill in some of the holes. We can have simulators that emulate real scenarios, and I think this can be very, very useful for large-scale simulations and agent-based modeling that I was hinting to earlier. So I do know the existence of some data. They might be limited in some respects if we want to build complex models that do also prediction of sophisticated behaviors and patterns. But I think I would argue that a merger between real data and simulated data can really help here.
Excellent, thank you. Good answer. So I'd like to toss this to our other two panelists as well. Rich, I'll offer to you first if you have something to add to the data question.
Sure. Just again, my focus is usually on social network data. So again, I do want to emphasize the API from Twitter for academic use is the entire archive, which is a huge step forward from the free API tier. If you're doing bot analysis, there are ground truth data sets available from Clemson University that help kind of get a data set you can train a model against. I think I'll stop there. That's good. Yeah.
Excellent. Thanks, Rich. And Barnett, do you have anything to add to the data question?
Yeah, very briefly. So I don't do a ton. I've done one or two projects using sort of social media data. So I don't want to comment on that. Rich is definitely the expert there. But for some of the problems I'm dealing with, that's often a real issue. There isn't ideal data. And in this case, in this particular problem, that wasn't just the case in terms of what academics had access to. That was also the case in terms of what the command had access to and what DHS had access to. And so we used IQs in large measure because it already existed and because it was something that the government was quite familiar with. But we spent far more time actually recoding the data to be useful for our analysis and really transformed it into something that it wasn't originally than we actually spent building the model and running the analysis that we ended up running. So I would just encourage folks to think outside of the box here. And is there extant data that can be recoded in a way that makes it useful to your problem or your question? Are there innovative proxies you can draw on if what you really want to measure can't be measured or hasn't been measured? And I think you can, if you spend more time thinking about those questions, you can probably do a lot more than you think you might be able to with just the data you may have access to. Thank you.
Excellent. Thank you. So I'm going to take another question from the audience. And Rich, I'm going to toss this one back at you first. It kind of builds on the data question. It's a tools question. So the question is specifically around tools that apply to analyze qualitative data from large text-based sources. So in your talk, you mentioned some tools. I wonder if you can talk just a little bit about tools that researchers might look at or applied researchers might look at as well to use.
Sure. So I'm a big proponent of the open source. I code in R, so I'm going to probably stick to that. Although for anything I mentioned here, there's likely a Java or Python implementation. So a lot of NLP in R is based on, I do latent derelict allocations, so LDA. There's freeware packages for that. Everything from simple term frequency through TF-IDF, LDA, and then up to BERT and more advanced NLP models are available open source wise. A lot of these have GUIs in a Shiny app as well. And then I would also, for qualitative NLP, I'm not a proponent of using sentiment analysis as a standalone, simply because I think it's problematic. But next to an NLP analysis of a conversation can be helpful. That is also in plenty of open source packages like Suzette and others in R.
Excellent, thank you. Barnett, I wonder if you have any specific tool recommendations, or maybe did you code the Bayes nets from scratch from yourself, or did you use an existing tool for those?
Yeah, so we did these from scratch in this particular case, but there are plenty of Bayesian packages in R for everything from network analysis to a whole host of pretty advanced statistical techniques. And so I agree with Rich. I'm a huge proponent of R. I will say I was having this argument last week with a colleague who is really advocating for Python. And I think the reality is they're very, very similar, as Rich indicated, in terms of what they can do. I think it really comes down to your initial training. And so I started using R for statistical analysis as a grad student. And therefore, when I learned how to program, it was obvious that I was going to start in R versus Python. But if you're coming from more of a CS background, you're probably going to be more inclined to start in Python, and you can do 95%, if not more, of the same stuff there. So I think it's more, what are you comfortable with? The nice thing about R or Python is there's amazing sort of communities online. So you don't have to know everything. Someone's already asked the same question that you've had on one form or another. There's probably 15 YouTube self-help videos on there. You really can teach yourself this stuff and do so pretty painlessly and pretty quickly.
Excellent, thank you. Carlotta, I wonder if you could comment on the tools that you and your students use when you're doing this research. How much from scratch, how much tools out of the box, or maybe algorithms from industry?
Yeah, so the work on I did work on community detection, network combined with text, and for community detection along with topic discovery. This was all done from scratch. by us and my students. I do work on deep learning models for tracking dynamics, behavior in networks, tracking communities, and role discovery, and predictions also of changes in at the community level for potential merger, splits, or growth and shrinkage. And there are plenty of libraries, of course, for deep learning, right? And mostly we use PyTorch. I also want to add a comment on the data question you had earlier. I want to add an orthogonal, I guess, dimension to that, the problem of validation. So often we have data available, but we don't have the ground truth. And that's can be a big problem. How do we validate our models, right? So I did some work, for example, insider trading, and you can build easily a network because all the data are available, and you can, scratch the data and build your networks. But once you find your patterns, right, how you validate what you've found. So that was a big issue for us in this project that we did. So what I want to argue here is that these kinds of effort needs to be strongly cross-disciplinary efforts where the computer scientists and the machine learning experts really work together next to each other with the domain experts. That can help us understanding whether what we discover is meaningful, and we can throw back that feedback in validating and optimize our models. So I wanted to throw that perspective out there.
Good, thank you. Thank you, very useful. So kind of a general question here that I'd like to throw to the group, and we'll start with Rich. Why is this so hard? I mean, you know, all the computational power and such, why can't you just run an algorithm on a bunch of data and spit out a network and say, this is what created this data, or this is how this network operates? So Rich, I'd like to maybe start with you, and you have a good bit of experience in applying these models. And why is this such a hard problem?
I'm trying to think of which cliche, like phraseology to start with here. I think it's going to be garbage in, garbage out for the analytics piece. So I think this is so hard because there's so much data and so little information. There's just so much noise in this environment writ large. It's very difficult. You're essentially trying to find a needle that's a little different colored than the rest of the needles in a pile of needles. No, not a needle in a haystack, essentially. And it also includes, quantitative and qualitative research aspects. There is what we call you hear the term computational social science a lot in this field. And it's kind of like a negation in terms, kind of historically. But I think we're coming together. We're bringing together a mixed methodology here in this science, and it's going to have growing pains. And neither the qualitative or quantitative aspects of this are independently stopping on their own to share the latest and greatest. So it's a constantly moving, attempting to merge target here, I think.
Excellent. Barnett, I'll ask the same question of you. What makes this so hard?
So I also had garbage in, garbage out in my notes, so I wholeheartedly agree there. I can expand on that just a little bit to say it's not just necessarily bad data, it's potentially really wrong and misleading data as well. And so I remember working very, very briefly consulting on a project that DoD was doing, and they were trying to make predictions in Iraq that using sort of population data from 2003. And they were doing this, by the way, 10 years later, or the better part of 10 years later. It turns out that during a sectarian civil war, you get a lot of internal and external movement. And that data was just totally wrong. So even though you could absolutely, from a method standpoint, build something that would spit out predictions and give you high confidence intervals, it was garbage. And of course it was garbage because I had some level of subject matter expertise that told me that things had changed between sort of when the data was collected and when the analysis was actually being done. And the model isn't smart enough to know that, and it never will be. And so I think for me, there is still a divide between the social scientists, and by the way, I'm a political scientist by training, and the folks with the technical skills for the most part to actually do the computational work. And I think that's seriously problematic. I think we need to do a better job of melding sort of the subject matter expertise, the deep theoretical knowledge about whatever it is we're trying to study, with sort of the hard CS and data science skills necessary to do it, so you can avoid sort of those easy mistakes like that Iraq project that I just mentioned. I think the other sort of thing here is the volume of the data also makes it really, really hard to sort of detect weird anomalies in the data. So like when I teach my undergraduate or graduate scopes and methods course, and it's sort of an introduction to basic statistics, we're dealing with sort of small data sets where they can actually take the time and they can read through every observation if they wanted to, or certainly they can very, very quickly generate some summary statistics and really drill down. That becomes far more daunting when you're talking about a data set with not 100 observations, but 100 million observations. You just can't do the same thing. And I think there's sort of a tendency within this community to say, hey, I'm not going to even bother to try and understand the data I'm dealing with. I'm just going to run some fancy models and trust the models. And I'm not saying everyone does that, but I have seen that before. And I think that's really dangerous. I make my students read a book called Weapons of Math, M-A-T-H, Destruction. We need something similar. We need sort of a code of sort of professional ethics or a best practices guidelines for this type of work. And I think it's doubly important when you're doing this in the national security space, because I've done sort of briefings to senior leadership that have been based on qualitative research and sort of quantitative research. And when I do qualitative briefings, I get really good engagement and really good feedback. When I do really rigorous sort of quantitative briefings, it's okay, yes, sir, he's a doctor, he must know. And that's dangerous. Hopefully I am doing it right and it's not a problem there, but that's really dangerous. So I think the onus is on us as the folks running this stuff to do better.
Thanks, Barnett. Very good. You remind me of the adage, how does it go? All models are wrong, some are useful. Something like that. Yeah, very good. So Carlotta, since you spend your days and nights trying to solve hard problems, how do you look at it? What's hard about the network discovery from data problem?
Yeah, so excellent points were made. I guess I'm gonna add a couple of comments here. I like to think that not all data are created equal, which is, you know, the similar idea behind finding the needle in the stack. But so there are actually data that may take the learning process towards the wrong direction, just because they basically break those underlying assumptions that the learning mechanisms are making. So understanding which portion of the network we should perhaps pay attention to, or which neighbors are most important to understand who I am and the best representation of an entity or of an individual or an organization, are important problems. I'm dealing with high dimensional data. We have been investigating this hub phenomenon where we see that there are data that are really breaking these underlying assumptions of the machine learning. So understanding these and really understanding the data, it's extremely important. And this go back, you know, to the garbage in, garbage out philosophy. Also, and this is of course general, but bias in the data is also a problem, especially when we are talking about the criminal domain, and where we make, you know, the model may make suggestions about decision. It's really important to understand the data, where they come from as much as possible, how they were generated, are there bias in the data, and what can we do to account for those biases, both in the pre-processing stage, if necessary, but mostly most cases that's not feasible. And so how do we account for that bias to do fair AI, right? Fair predictions. And so how do we account for that bias during the learning process itself? So those are all elements that make the whole process quite challenging.
Excellent. So Carlotta, you kind of seeded my next question, which I'll first throw at Barnett and we'll work around again. You mentioned data taking a model in the wrong direction. So I'm curious about the risks of essentially algorithmic discovery of networks from data. And, possibly it's an adversary who knows your model and is deliberately doing that data, or possibly it's just a product of the data. So maybe to Barnett, generally, what are the risks of doing this, where we're running computation on a bunch of data and we spit out answers? I think everyone's kind of alluded to pieces of this. I'd like to just call it out and ask if you have ideas on what do we do to mitigate these risks as well.
Yeah, so the notion that you just threw out there, sort of an adversary purposefully sort of corrupting our data or providing us with bad data, is not all that far-fetched. And that's really scary, because then they can sort of force us to not just make the wrong inferences, but make precisely the wrong inferences that they would like us to make. And there's a piece of old Soviet doctrine called reflexive control. And it's basically, how do I make my opponent do something that's perhaps not in their best interest, but certainly do what is best for me without fighting? How do I make them come to this decision on their own? And this is obviously something that was developed early on in the Cold War, well before anyone was running models like this, like these. But what I think sort of the 21st century and sort of the cheap compute power that we have today now has done is made it much, much cheaper to sort of mislead and do some of this reflexive type control type stuff if you wanted to, and you could get into sort of your opponent's data supply, which frankly, if we're using open source data from social media or so on and so forth, that's really, really easy to corrupt. I don't know if anyone's saw this on the news, but how many billions or millions, I apologize, I didn't actually read the article carefully, of fake sort of product reviews did they just find in that database for Amazon? I mean, that's brilliant to me. You're changing sort of purchasing behavior in a similar way by corrupting the data. And obviously that's for sort of commercial gains, for inferior products, not necessarily a state adversary, but I think the parallel exists there. So we need to do a better job with sort of data security and validating sort of the veracity of the data we're using before we just sort of blindly run things. But even beyond sort of malicious intent by a competitor or an adversary, I think you're right. There is a massive risk that we're going to be led the wrong way because we're using bad data and we're blindly making inferences based on that. So I just want to reiterate sort of the point I made about integrating the data analytics with some detailed sort of theoretical knowledge and subject matter expertise. And I think that's probably that's a non-technical way of dealing with this, but I think it's one really good way of guarding against some of these sort of extreme risks. And let me just give you sort of another example of where this sort of comes into play. When we were looking at IQ's data, and we were looking at it in Colombia, and the model had miscoded so IQ's is all based on sort of Texas data, and it pulls in news reporting from around the world in multiple different languages. And it had miscoded Latin American sports reporting as sort of kinetic engagements, because it turns out if you're a soccer, or in their parlance, a football fan, that reporting uses really martial language: attack, defense, etc., shoot. And so, of course, soccer matches aren't fighting, but the model thought it was. And if you didn't look closely, you would have missed that, and you would have massively biased sort of the results. But unfortunately, fixing this actually gets far more complicated, because my initial reaction was, hey, let me just drop any sort of episode that any observation that uses sort of this type of language that also includes the word goal or score or whatnot, soccer-specific terms in the article. But that actually doesn't necessarily work, because you get tons of rioting and tons of actual violence around soccer games in many parts of the world, which we might actually care about. And indeed, Honduras and El Salvador actually fought a war that was touched off by a soccer riot.
Excellent, thank you. Good example.
Thank you.
Carlotta, since your comment kind of seeded this question, I'll toss it back to you to talk a little bit about some of the risks of doing discovery this way, and how we might mitigate some of those risks.
Yeah, so with respect to the bias in data or possible attacks and interjections, definitely methodologies that enables us to guard as much as possible the data to begin with are definitely desirable. But back to the idea of one overall approach that we are kind of also taking in other context is if we can try to take a generative approach to the problem, right? Where you can try to rediscover the underlying process that generates the data, then you can possibly identify also malevolent intrusion in the data. And this combined also with an exemplar-driven approach that enables us to understand the best exemplars to leverage in order to come up with this generative modeling, I think can be very useful. To contextualize things a little bit better, for example, a framework like in deep learning in variational autoencoders, which can also be built in an exemplar-driven approach, can be useful. You basically learn driven by exemplars that you select from the data and embedding that I guess better emphasizes the intrinsic features of your data. And it has the additional power of being able to actually generate data according to those underlying distribution. I think approaches of these kinds can help overall discover the underlying process generates the data and therefore isolate those bad data that we want to filter out.
Sure. Thank you, Carlotta. Rich, do you have some comments to add to the question about risks? Yeah.
Two quick things. I really like the soccer example. It reminded me of something as well. Goal and score is it's not a very common event in those games, low scoring events. So it might not be carrying the weight of the word that would differentiate it. I'd recommend maybe a mixed methods approach that takes a single still frame of video, and does an image analysis to make sure like it can classify it as green for soccer in this case and set a set of rules that would kind of help that out. So mixed methods that includes image classification and your text analysis of the script would be helpful. And then the second part is from a national security perspective, it's important I want to emphasize that our adversaries are doing this intentionally, and this is military deception, and the tenets across the board they remain the same. The Russians especially have a history of seeding the environment with a lot of noise that would be of interest to the United States over here while doing something over here, for instance. They also have a lot of experience with flooding an environment to prevent a conversation from happening in the first place, which leads you to believe that it's not an important topic even though it is. So there's a whole bunch of stuff. I guess my thing on that second part is you don't know what you don't know, so assume the first thing you see from an adversary is what they want you to see, and that comes from that.
Excellent. And Barnett, I think you may have had a follow-up on this one.
Yeah, just one thought that came to me. So at the University of Maryland, we maintain the Global Terrorism Database, which is about 200,000 observations. And we're human. We create the team that does that makes mistakes. And I think, but those get corrected, and they get corrected pretty quickly because that data set's open source, it's out there, it's used by a lot of people. So I've actually seen sort of their generic inbox where people write in and say, hey, I found an issue with the coding here, and so on and so forth. And so there's a tendency in the national security space to classify everything, or to place more emphasis on classified data sources versus unclassified ones. And having worked with both in sort of general terms, there's a real advantage to sort of this crowdsourcing of the identification of problems in the data that occurs when you let a bunch of nitpicky academics like myself look at your data and play with your data and so on and so forth. And I realize that's not always possible in this space, but I do think there's real value to wherever you can, making your data out there, putting it out there, and letting others try and find those issues, because they will.
Excellent, thank you. So I think we have time for one or two more. The one I'd like to ask maybe turns this on a little bit to a positive side here. So Carlotta, I'll start with you, but the question is about what's coming down the pipeline, what's on the horizon. So are there computational techniques, hardware, software, or something else algorithmic that are on the horizon coming down the pipe that you're excited about that you think will make a considerable difference in this work that we're trying to do?
Okay, so great question. I'm a sort of a believer of hybrid methods, as I hinted in my presentation. I do think that data mining or data-driven approaches cannot do it alone. And combining closely data-driven approaches with domain expertise can be really useful. So, you know, I would like to, I think that an example, as I hinted earlier, is when we marry data-driven approaches with the domain expertise to train complex and large-scale agent-based modeling. And I would like to point out that these kinds of technology has been used successfully, right? For example, in the social sciences, there have been many areas of the social sciences that have been revolutionized through agent-based modeling and multi-agent systems. They've been used for studying new economies, for studying the financial markets, and they've been used for the current epidemic. I think the time is ripe now to use these kinds of large-scale modeling for these kinds of networked data. They can be really powerful. Now, a drawback or a problem with these large-scale models is that they have tons of parameters, right? And often we don't know how to tune these parameters. We don't know their values. But so there I think where the machine learning data-driven piece of the system could really help. It could really inform these large-scale systems on understanding the behaviors of the agents, how these agents operate. And then we're going to let the simulation build the networks and their interactions to see which macro level phenomena can arise from these complex agent interactions. And an interesting element to this is that we can use known data also to do automated validation, back to the problem of validating results. And I think this can be very powerful once we marry these two systems, data-driven and large-scale simulations. So, yeah.
Yeah, thank you, Carlotta. Good. So Rich, I'll ask you next if there are things coming down the pipe that you're particularly excited about that you think might make a difference.
Yeah, I think what I'd like to focus on is the real world impact piece I touched on before, specifically the distribution of malware via networks. Just to clarify what I mean by that, I'll tell a story. When a couple of years ago, I did a demonstration for the Capital One Arena folks here in DC. I had the general manager of the facility log on to Twitter, click a tweet that I sent, a direct message to him while his phone was on the installation's Wi-Fi system. He clicked the link in the tweet and the lights turned off. Took about 10 seconds. So that was obviously a pure pre-staged demonstration for impact, but it did its job. And what we're seeing a lot now is the use of URLs that intentionally were originally designed to save space in things like tweets for character counts, now being used to obscure a URL, which will eventually say take you to the news story that the person posted about that you clicked on. But there's a bounce page somewhere in there that's distributing this malware. So being able to track that in as fast a time as possible gives us a couple things. Mitigation opportunities are real at that point. It's not just narrative, and I'm not saying that narrative contesting the narrative is not a real fight. But when it transitions to real world, the impacts become a bit less gray and a little bit more black, right? And then. So finding those early on is important, and it also is an exciting time in this space because the malware is a piece of attribution and kind of forensics that you can take a look at. Where did this come from? What's the code comment in? Have we seen this looked up on things like foreign stack overflows and things like that? So there's a lot of new opportunities to label attribution, which can be extremely helpful in the national security fight in this space.
Excellent, thank you. And Barnett, can you say something about things that you're excited about coming down the pipe that would make a difference?
Yeah, absolutely. And so this is a topic I know very little about, but that I'm actively sort of investing some time into learning a bit more about. And so I've gotten interested recently in sort of generative adversarial networks, or GANs. And I think this could be a cool sort of approach to I mean, it's a neural network technique, and the sort of way this works is you train a generative model to come up with sort of new examples based on some of the training data, and then you train in parallel a discriminator model that tries to classify these new observations as either real or fake. So you're setting sort of two unsupervised models against each other and perhaps getting better results as a result of sort of this competition. And sort of intuitively, I really like this idea because it sort of mirrors how sort of humans behave. And right, if we're competing against someone who does similar stuff and we're trying to get to the publication first or whatever else, we tend to push ourselves to do better work. And so I don't know, I think this could be really cool. I have not had a ton of experience with sort of neural networks in more generally speaking, but I definitely see that that's the writing on the wall in terms of where a lot of people in this space are going. So I don't want to overpromise here, but it's something I'm looking into.
Excellent, excellent. Thank you. Good. So we have just about 5 minutes left, maybe 4.5, something like that. So what I'd like to ask is for each of the panelists, if you can, in about a minute, anything that you'd like to leave our audience today with, and we'll go back to our original order. So I'll ask Carlotta first if there's something you'd like to leave our audience today with.
Yeah, I'll be brief. I want to emphasize the fact that I think that this endeavor will require an effort, a cross-disciplinary effort, where a social scientist, a domain expert, computer scientist, machine learning expert, expert in simulations, and the modelers really need to come together and work closely with one another. And one last comment is networks are great, but also have their limitations, and perhaps we should be, aware of this. So with a network, I have entities, nodes, and edges, and an edge can only characterize, dual relationship, a relationship between two entities. In my experience, for example, when I worked with insider trading, we had a need to represent multi-way relationships. And so we went beyond networks, and we actually used hypergraphs, and where the hyperedges actually enables us to represent multi-way relationships, which enabled us to find patterns, interesting patterns of suspicious behaviors that were not possible if we did use networks. So, as a final remark, something to keep in mind, we can also go beyond network representations of our data.
Great, Carlotta, thank you. Thank you. Rich, final thoughts?
Sure, a couple things. Again, from social network analysis perspective and the national security infrastructure perspective, analytics and algorithms and machine learning and AI are not in the near future going to give you an answer. It's going to cut down on the work that your SMEs and experts already have. And I think that just is another way of saying what Carlotta just said. This SME human in the loop piece and I'm a quantitative guy. And to have to say that hurts, but it's true. Number two, there is no data that can't be thought of as a graph and brought together that way. So I encourage everyone to use graph databases to cut down on the volume and size in terms of finding relationships between it. And then third, as we move forward, this is going to continue to evolve. So we will never be able to say that we're done advancing this science. And I think that's kind of a cool thing.
Excellent, thank you. And Barnett, final thoughts?
Yeah, so I completely agree with what was said before me. Right, I think there's a need to sort of combine diverse expertise. There's absolutely a need for the human to keep a human in the loop. As Rich just said, I think you can do impressive things in terms of reducing workload, and we're seeing this with sort of full motion video or FMV analysis right now. If you can sort of cut down the analyst workload by 95% and cue them in on what they need to actually review, that's a huge cost savings for the government because this is a really expensive activity. I think there's a need to be honest about what the data looks like and what you've done with the data and how confident you really can be in the results beyond just what the model spits out. And I think there's one thing that hasn't been mentioned yet that I think is really important. The best models, the best analysis, it's all useless if you can't articulate the results in a way that are understandable or that are trusted by whomever the decision maker is, whoever the end user is in this space. And so I think we probably need a better job, this is putting me putting the professor hat back on, not just teaching people how to run these models, but how to tell a story with data and how to make the results approachable to a senior leader who has never had any formal training in this space, but that nonetheless is being asked to make really consequential real-world decisions based on analysis that he or she probably doesn't fully understand and through no fault of their own.
Excellent, thank you. We're at our time. I deeply appreciate our panelists taking your time to share your expertise and your thoughts. Very much big thank you from all of us. Also, thanks to all of our audience for attending, for the questions, and for your interest in what we're doing. Please join us in about 15 minutes. The COEs have a showcase. All the COEs will have projects and researchers available. Picture a big auditorium with a bunch of booths and people showing off all their cool stuff. That's what the event is at 4 o'clock, runs for about an hour and a half. You can get time to talk directly with the researchers and the COE folks. So thank you again. We hope you enjoy the summit.